Hi friends, today we start lecture 64 on our helicopter dynamics course, and today we are going to talk about flexible lag bending. I'm Dr. Ranjan Ganguly. Now previously we studied rigid blade in lag, so we derived the equations for the rigid blade in lag. Now as you can immediately understand, this is not going to be a very good model for realistic helicopter blades because they do bend in the lag direction. So what you would want to do is just similarly to the way we do for an actual beam, we want to look at the chord-wise bending or the in-plane bending of the rotor blade. So this is essentially known as lag bending. So let's look at the picture of a section where forces are acting in this lagging blade. So this is your blade here, and there is a rotation speed in this particular direction. Now we'll consider two sections here, a section at a distance r and a section at a distance rho from the hub or the root of the blade. Now the forces which are going to act at a small point at distance rho are going to be the centrifugal force, the inertia force, and the aerodynamic force. Also, VR is the lag deflection at r and V rho is the lag deflection at rho. Let's take a more detailed look of this section because this is important to get some of the moment arm, especially for the centrifugal force. So now we look at the blade here. The blade is essentially this curve, which is a representation of the fact that the blade bends in the chordwise direction. Now if we look at geometry and we look at 2 points here, we can see this triangle, and from this triangle we can write that V rho divided by rho equals VR plus delta divided by R. So here I'm taking the fact that this angle is given here, and if I take the tan of this angle, for example, the tangent of this angle, it's going to be V rho by rho, and it's also going to be VR plus delta by R. Now from this equation we can obtain delta as R by rho V rho minus VR. Now why we are interested in this delta is because the centrifugal force is going to act at a certain point here, and the arm or the moment arm for this centrifugal force is going to be given by this value delta. So let's look at each of these forces separately and look at the moment arm. We are doing this because our objective is going to be to get the moment at radial length r. So we start with IF here. Now IF is going to act in a direction which opposes the direction of motion of this lag. So it's going to be m v double dot into d rho, and the arm is going to be rho minus r because this is rho here, this is r, so this exactly is the distance from location r to the point here. So remember, we are going to take the moment at the section r. Okay, so we took care of one of the forces here. Now we looked at the next force, that's the centrifugal force acting at this section. So the centrifugal force is going to be m rotation speed square rho d rho. Rho is the distance of this point. So that's the usual expression for centrifugal force. Now this arm is the value delta which we calculated before. So you can refer to that slide before, and so that's going to be the moment arm. Because now what's happening is centrifugal force is in a straight line from the root, but the beam has a bended profile, or the beam is a curve, it's not a straight line. And the distance between the straight line and the beam or the bended profile is this particular value delta. So that is actually the moment arm here. Finally, we look at the AF, which is created by the fluid mechanics which acts on this blade. Remember, the blade is an airfoil section. So it's going to generate a force Fx into d rho. So Fx is related to the drag component predominantly, and so that's going to act in this direction. So it's going to try to increase the lag motion, and the arm again is going to be rho minus r. So that's the distance which is the arm of this force. Now we take all these forces and we get the lag moment at section r. Now some of these forces are going to try to increase the lag, some of these forces are going to try to decrease the lag. So if you saw the previous diagram, essentially Fx is positive and the component due to V double dot and the component due to centrifugal force are both negative. So this is the equation or expression we get for mzr, and that's the lag moment at section r. Now we are going to use this moment in the equation for bending moment. That is, relate mz to eiz and v. Now to do that, one of the things we will do later is we are going to differentiate some expressions, and so we use the Leibnitz theorem here, which essentially tells you that if phi is a function given as follows. So essentially there is a function here and this is integrated between points u1r and u2r, then d phi by dr can be calculated by this expression here. So essentially what happens with this expression is that you sometime differentiate f, and you also need to differentiate these bounds in the integral. So you need to differentiate u2 and u1, and you need to calculate the function value at u2r and u1r. So if you do that, you can obtain the derivative of the function phi. So again, just to recapitulate, this is the moment at section r. Now we get to the bending equation, the beam bending equation, that is mz is eiz d2v by dr2. Now here Iz is the moment around the z-axis, so that is going to be x squared dA around the section, and mz is the moment of forces around the z-axis at station r. So taking the derivative of the moment, so we take two derivatives here and then we get an expression in this form after we use the Leibniz theorem. So now if we look at this equation carefully, we will see this is somewhat similar to the flap bending equation, but there is one extra term. So of course this term involving EIZ is the well-known flexural stiffness term. This term is a centrifugal force term, and then inertia force term is coming from mv double dot, but then there is an extra term here which is the vertical component of the centrifugal force. So essentially this entire equation needs to be solved, and of course, as you realize just by looking at it, this is a non-trivial equation as far as solutions are concerned. One thing we immediately do whenever we encounter a complicated equation is we try to simplify it. So if we have a free vibration problem, then your fx could be put to 0, but even then this equation would be very difficult to solve because of the presence of this integral sign here. Now we don't have an easy method to solve it, but let's look at the boundary conditions. Now the boundary conditions are similar to what you have for a flap equation and for a hingeless plate. So if we look at a hingeless plate, at r is 0, v is 0, dv by dr, or the slope is 0, and at r equals capital R, which is the tip of the blade, mz equals eiz d2p by dr2 is 0, that means the moment is 0, and also the next derivative, which is the shear force, is also equal to 0. So these are boundary conditions we are familiar with, and one of the things we can do is that we are not able to solve the rotating beam equation in lag, but we could take the non-rotating equation for a uniform lagging blade. We could obtain mode shapes and frequencies, and we could use methods such as the Rayleigh-Ritz method or the Galerkin method or FEM to solve this equation, methods with which we are familiar and which we have discussed in the course before. So again, just to recapitulate, if you were to get the solutions for the non-rotating vibration, you would get the non-rotating natural frequency in this form. They would be dependent on root EIZ by MR4, and these lambda j's are essentially obtained by solving the characteristic equation for a cantilever beam, and this phi j r constitutes the mode shape for a hingeless blade or for a cantilever beam. So again, we can use this as a beam function in Galerkin method or Rayleigh-Ritz method for finding the frequencies for a rotating elastic blade in lag. So today I am going to stop here, and in the next class we are going to look at how the FEM formulation will change when you have lag bending. Remember that there is an extra term now in the equation which is essentially coming from the centrifugal force, and that's something we need to capture. So I'll stop here. I will see you in my next video. See you soon.